Economic calculus has a precise spatial objective, locating the absolute optimal state of a system. Whether you are maximizing profit or minimizing production costs, the math behaves like a coordinate system mapping a physical landscape. When a business has infinite resources, we call this unconstrained optimization. Variables scale freely, generating a vast surface of outcomes. But the real world introduces strict boundaries, like budgets. This is constrained optimization. You are trapped where the budget slices the topography. We must map the multidimensional surfaces, apply the constraints, and mathematically collapse the dimensions to find a single, definitive answer. Multivariable calculus provides the mechanism to do this. It is a set of tools for navigating the topographical map of financial reality. Let's examine an unconstrained multivariable profit function. Here, a firm's total profit, represented by the symbol pi, depends on the production volumes of two distinct products, Q1 and Q2. To find the absolute peak of this function, we apply the first-order condition. This involves finding where the slope of the surface is exactly zero. Because we have multiple variables, we use partial derivatives, which requires isolating one variable's rate of change while treating the other variable as a frozen, static number. First, we take the partial derivative with respect to Q1, holding Q2 constant. The resulting derivative equation dictates the slope specifically along the Q1 axis, which levels off as it reaches the critical point. Next, we do the inverse. We take the partial derivative with respect to Q2, holding Q1 constant. This gives us the slope along the perpendicular axis. Setting both of these partial derivatives equal to 0 allows us to identify a specific location on the grid where the slope is perfectly flat in all directions. This creates a system of simultaneous equations. Solving them reveals the exact coordinates where these slopes intersect at 0. The math yields a Q1 of 100 and a Q2 of 300. We have located a critical point on the profit surface. However, the first-order condition only proves that the surface is flat at this specific location. We cannot assume a flat point is actually the absolute peak of our profit. Relying exclusively on first-order conditions in a multidimensional environment is insufficient for a complete analysis. A mathematically flat tangent plane could represent the bottom of a valley, indicating minimum profit, or it could be a deceptive saddle point, curving upwards in one direction and plunging downwards in another. To verify the true shape of the curvature, we use the discriminant rule. This formula uses second-order derivatives to rigorously test the concavity of the surface at our critical point. We calculate the second-order partial derivative for Q1, which returns a value of -4. We calculate the second-order partial derivative for Q2, which returns a value of -2. Finally, we calculate the cross-partial derivative, which captures how the two variables interact with each other, yielding -2. Evaluating the formula, -4 times -2 minus -2 squared simplifies to 8 minus 4. The final discriminant value is exactly 4. Because the discriminant is greater than 0 and the second-order derivative of Q1 is negative, the surface definitively curves downward in all directions. The discriminant rule acts as an essential mathematical check. It proves that the coordinates 100 and 300 form a true local maximum, protecting the analyst from costly false positives. Now, consider a model for constrained optimization. In this scenario, consumer utility, U, is determined by multiplying quantities of food and clothing. In reality, consumption is limited by capital. We have a budget of $120, food costs $15 per unit, and clothing costs $12 per unit. This creates our mathematical constraint equation. 15F plus 12C equals 120. Visually, this budget acts as a rigid wall, slicing through our utility surface. Our objective is no longer finding the peak of the entire unconstrained surface. We must find the highest possible elevation exactly along that sliced path. To embed this physical boundary directly into the objective function, we use the substitution method. Step 1 is algebraic rearrangement. We take the constraint equation and isolate the food variable, redefining it as f equals 8 minus 0.8c. Step 2 is the substitution itself. We take this new definition of food and plug it directly into the original utility equation. Expanding the new equation gives us u equals 8c minus 0.8c squared. This chart shows the resulting two-dimensional parabola. By fusing the equations, we have mathematically eliminated the food variable, simplifying the problem. This algebraic substitution forces a dimensional collapse. We have transformed a complex three-dimensional surface problem into a simple, solvable two-dimensional curve. Solving this collapsed two-dimensional function requires returning to single-variable calculus. We take the first derivative of the collapsed utility function, yielding 8 minus 1.6c, and set it equal to 0 to locate the peak. Solving this simple linear equation reveals the optimal amount of clothing, c equals 5. We verify this is a true maximum using the second-order derivative. The result is negative 1.6, confirming a downward curve at the peak. Now we execute the back substitution process. We take our optimal clothing value of 5 and plug it back into our isolated constraint equation. 8 minus 0.8 times 5 leaves us with the optimal amount of food, F equals 4. Multiplying 5 units of clothing by 4 units of food yields our final answer. The absolute maximum utility achievable under this budget is exactly 20. Looking back at the three-dimensional geometry, those coordinates map exactly to the highest possible point along the exact slice dictated by our constraint. Partial derivatives and algebraic substitution are more than abstract rules. They are precise instruments for navigating multidimensional models. By mathematically integrating constraints into objective functions, we can determine the exact allocation of resources required to achieve an optimal state within economic systems.